Hello everybody. In this video we're going to begin with Chapter 5, Proofs. These are the learning objectives of the chapter. So you should be familiar with the skills essential to read and practice abstract mathematical concepts, logic basics for proofs such as statements, negations of statements, and compound statements, the concept of proof, and several proof procedures like direct proofs, proofs with the contrapositive, contradiction, or counter examples, and finally, writing and understanding proof by mathematical induction. We will start with section 5.1, Basic Laws and Simple Proofs. Logic Basics. The most vital notion in mathematics is that of proof. In mathematics, it is a process of establishing the validity of a statement, especially by derivation from other statements in accordance with principles of reasoning. Mathematicians use deductive reasoning to develop and extend a theory by drawing conclusions based on statements accepted as true. Proofs are essential in mathematical reasoning because they demonstrate that the conclusions are true. Generally speaking, a mathematical explanation for a conclusion has no value if the explanation cannot be supported by an acceptable proof. It is not enough to test the statement with a few examples. So now let's focus on example 5.1, and it says, prove that the sum of any two odd integers is an even integer. So let's take a look at the solution. The first thing you need to do, as you can see here, is define what even and odd is. So it would say an integer is even if it can be written in the form 2 times k for some integer k. An integer is odd if it can be written in the form 2k plus 1 for some integer k. Then the proof follows straight from the definition. So this is a direct proof. Let m and n be any two odd integers. We want to show that m plus n is an even integer. Then we say, by definition, an integer is odd if it can be written in the form 2k plus 1 or 2k minus 1 for some integer k. Thus, there exist integers r and s such that m is equal to 2r plus 1 and n is equal to 2s plus 1. Add m plus n, so m plus n is going to equal 2r plus 1 plus 2s plus 1, which equals 2 times r plus s plus 1. Because r plus s plus 1 is an integer, this proves that m plus n has the form 2k and thus is an even integer. So now let's take a look at a definition. A statement or proposition is a sentence that asserts a fact that is either true or false, but not both. So let's take a look at example 5.2. Which of these are statements? A. Vienna is the capital of Austria. This is a statement, which happens to be true. 12 is a prime number. This is a statement, although it's false. 2 plus 3 equals 5. That's a true statement. Euler was a great writer. This is not a statement. This is an opinion. It could be either true or false. 2 plus 3 equals 6. This is a statement, although it's false. And F, n plus 1, is less than or equal to 15. This is not a statement because it can be either true or false. It depends on the value of n. This is what is known as an open statement. So now we're going to take a look at table 5.1, which is a truth table for statements P and not P. So this is P, and this symbolizes not P. So obviously when P is true, not P is false, and when P is false, not P is true. There's some similarity between logical statements and set theory. We could use as an example this. Statement P, n is an even integer. So that means that n belongs to the set of even integers. Or you can see it in the Venn diagram. So here we can see E, which is the set of even integers, and complement of E, which is the set of numbers that are not integers. And U is the universal set. So if P is true, then n belongs to set E. If P is false, then not P is true, and then n belongs to the complement of E. In other words, n is not an even integer. So now let's take a look at example 5.3, and it says, find the negation of each of the following statements and write them in simple English. For letter A, statement P, Kevin is looking for a new car. For letter B, statement Q, 142 is a perfect square. And for letter C, statement R, Tim walked his dogs 20 kilometers on Sunday. Let's take a look at the solution. For letter A, statement not P, it is not the case that Kevin is looking for a new car, or expressed in simpler words, Kevin is not looking for a new car. For letter B, statement not Q, it is not the case that 142 is a perfect square, or simply put, 142 is not a perfect square. And then statement C, not R, it is not the case that Tim walked his dogs 20 kilometers on Sunday, or simply expressed, Tim did not walk his dogs 20 kilometers on Sunday. Okay, so now let's take a look at some definitions. Let P and Q be statements. The conjunction of P and Q, denoted by this, is the statement P and Q. The conjunction P and Q is true when both P and Q are true and is false otherwise. We can see that in this truth table here. When P and Q are both true, then P and Q is true, otherwise it is a false statement. The disjunction of P and Q, denoted by this, is the statement P or Q. P or Q is true when at least one of P or Q is true. So notice that here they are both true, therefore P or Q is true. P is true, therefore P or Q is true. Q is true, therefore P or Q is true. And it is only false when both are false. Now, the conjunction and disjunction ideas can be demonstrated in Venn diagrams. For the conjunction to be true, the points have to be in an area occupied by both P and Q. So it's the intersection of P and Q. Whereas for the disjunction, it suffices to be in any of them. So this is similar to the union of P and Q. It's very important, though, to state that in set theory, P and Q have some relationship, while in logical statements, they do not have to be connected. The only thing that counts is a respective truth value. In logic, the word but is sometimes used instead of and in a conjunction. For example, the statement, the car is running, but the back door is open, is another way of saying the car is running and the back door is open. While and although are also used. Now let's take a look at example 5.4. C is the statement, 41 is composite. This is obviously false. And M, 45 is a multiple of 5, which is true. C is false and M is true, as we just said. Thus, 41 is composite and 45 is a multiple of 5, written using connectives as C and M, is a false statement. While 41 is composite or 45 is a multiple of 5, written using the connectives as C or M, is true. Also, the statement either 41 is composite or 45 is not a multiple of 5, written using connectives as C or not M, is false because they are both false statements. So now let's take a look at example 5.5, and it says find the conjunction and disjunction of the statements M and N, where M is the statement. Tim's PC has more than 100 gigabytes free hard disk space, and N is the statement. The processor in Tim's PC runs faster than 2 gigahertz. So the conjunction would be the condition M and N. So in order for this to be true, both statements have to be true. Any other case would make it false. So both Tim's PC has more than 100 gigabytes free hard disk space and the processor in Tim's PC runs faster than 2 gigahertz have to be true in order for this to be true. Let's talk about the disjunction, which is M or N. In this case, the only way this can be false is if both statements are false. So either one can be true. It would make this disjunction true. So if either Tim's PC has more than 100 gigabytes free hard disk space is true, or the processor in Tim's PC runs faster than 2 gigahertz is true. So now we're going to look at several other important ways in which propositions can be combined. Specifically, we will see how statements can lead from one to another. The statement, if P then Q, also written with this simple arrow, is called conditional because if P then Q asserts that Q is true on the condition that P holds. It's also known as an implication. This is the truth table for the conditional statement, if P then Q. So notice that if both P and Q are true, if P then Q is true. If P is true but Q is false, then if P then Q is false. If P is false but Q is true, then if P then Q is true. If both statements are false, then if P then Q is true. The conditional parallel is shown in the diagram, which demonstrates the idea of subset. This is a very important tool that helps later in using contrapositives in proofs. P is a subset of Q is similar to if P then Q. Notice that for P subset of Q to be true, then when X belongs to P, X must also belong to Q. As discussed earlier, if P then Q in set theory is similar to when we talk about P being a subset of Q. Notice that X, in this case here, represents the first row of the truth table. Because X belongs to P and X also belongs to Q, therefore P is a subset of Q. Y, on the other hand, represents row 3, where Y is not in P, but it is in Q. Z, on the other hand, represents row 4, where it's false for both cases, but true for if P then Q. And then finally, the case of U would be the second row, where we notice that although U belongs to P, it does not belong to Q, therefore P is not a subset of Q. Conditional statements play such an essential role in mathematical reasoning that a variety of terminology is used to express if P then Q. So we have if P then Q, or P implies Q, P only if Q, Q when P, Q is necessary for P, P is sufficient for Q, Q if P. Now let's focus on example 5.6. Consider the statement your teacher makes to you. If you get 80% or more on your final exam, then you will receive a course grade of 7. The only time you feel cheated is when you get more than 80% on the final, but did not receive a grade 7, which is precisely the second row in table 5.4. Some people are confused with rows 3 and 4. How can a false statement lead to a true one? So this situation is similar to when you get less than 80% but still receive a grade 7, which would be this case. This may happen because your grade depends on many factors other than the final exam. Row 4 is equivalent to you getting less than 80% and not receiving a 7. To further understand this, let's look at example 5.7. Suppose you tell your younger brother, if the concert is sold out, I will take you to the movies. The promise is broken, the conditional sentence is false, only when the concert was sold out. The antecedent is true, and you did not take your brother to the movies, so the consequent is false. This is row 2 of the truth table. In all other situations, the promise is true. If there were no tickets left, like in row 3 and row 4, we don't say the promise is broken regardless of whether you decided to go to the movies or not. The promise is also kept in the situation where the concert is sold out and you went to the movies, which is row 1 of the table. Our truth table portrayal for P then Q captures the same type of statements that we've used in mathematics. For example, if we think of X as some fixed real number, we know that if X is greater than 10, then X is greater than 5. But notice that the converse of this is not necessarily true. That is, if X is greater than 5, then X is greater than 10 is not necessarily true. So this is where we introduce a related concept, which is that of equivalence. And this is read as P if and only if Q. So notice that for P and Q to be equivalent, we have to have necessarily that if P, then Q, but also if Q, then P. This is the truth table. Notice that the only circumstances where this is true is where both statements are true or both statements are false. So notice that we can say this as P if and only if Q, sometimes written as P if Q with double F, or P is necessary and sufficient to Q. Let P and Q be statements. The converse of if P then Q is if Q then P. The contrapositive of if P then Q is if not Q, then not P. So now let's focus on example 5.8. And it says, write both the converse and the contrapositive for each statement below. In each case, determine whether the given statement is true or false, state whether the converse is true or false, and state whether the contrapositive is true or false. So let's start with letter A. So notice that the converse is going to be if 6 is a composite number, then 5 is less than square root of 26. By the way, these statements are both true. The contrapositive is if 6 is a prime number, which is false, then 5 is greater than or equal to 26, which is also false. So let's go back to the initial statement, and we can see that this is true. 5 is less than the square root of 26, and 6 is a composite number is also true. So that means that the statement is true because of the truth table in the first row. The converse is also true, same first row in the truth table. And the contrapositive is true because both statements are false. Therefore, the contrapositive is true. So now let's focus on B. And it says if 5 is greater than or equal to the square root of 26, which by the way is false, then 6 is a composite number. This is a true statement. The converse of this would be if 6 is a composite number, true statement, then 5 is greater than or equal to square root of 26, false statement. The contrapositive, if 6 is a prime number, false, then 5 is less than the square root of 26, which is true. So we have that the statement is true. Why so? From row 3. Notice that if P is false, or the first statement is false, and the second one is true, then if P then Q stands. The converse is false. Why? Look at row 2 of the truth table. First statement is true, but the second statement is false. Therefore, it's false. The contrapositive is true from row 3 of the truth table because the first statement is false, but the second statement is true, as we can see here. So now let's take a look at C. And it says, if 5 is less than the square root of 26, which is a true statement, then 6 is a prime number, which is false. So the converse is going to be, if 6 is a prime number, false statement, then 5 is less than the square root of 26, true statement. The contrapositive, if 6 is a composite number, this is true, then 5 is greater than the square root of 26, which is false. So the statement is false. We can see this in the second row of the truth table. True, false, therefore false. The converse is true from row 3, false, true, therefore true. And then the contrapositive is false from row 2, because first we have true and then false, therefore false. And then last but not least is letter D. And it says, if 5 is greater than or equal to 26, which is a false statement, then 6 is a prime number, also a false statement. So the converse would be if 6 is a prime number, false, then 5 is greater than or equal to 26, false as well. The contrapositive would then be if 6 is a composite number, which is true, then 5 is less than the square root of 26, which is true. So notice that everything here is going to be true. Statement D is true from the fourth row of the truth table. Both statements are false. Therefore, if P then Q is true. The converse is true because it's just going to be, again, the fourth row of the truth table. And then finally, the contrapositive is true. So that would be the first row of the truth table. So in the previous example, you might have noticed a pattern, and that is that if P then Q is equivalent to its contrapositive, if not Q, then not P. Whereas if P then Q is not equivalent to its converse, if Q then P. And we can use the truth tables to examine these statements. Notice that in the column of if P then Q, we have the equivalent results for the column of if not Q, then not P. Whereas it is not the case in this other column with the converse, if Q, then P. The Venn diagram to the left can be used to imitate the contrapositive case. When X does not belong to Q, therefore not Q, implies that X cannot be in P, therefore not P. So that can only mean that P is a subset of Q, or if P, then Q. So now we're going to talk about valid arguments. Later in this chapter, we're going to study proofs. Proofs in mathematics are valid arguments that establish the truth of mathematical statements. By an argument, we mean a sequence of statements that end with a conclusion. By valid, we mean that the conclusion or final statement of the argument must follow from the truth of the preceding statements or premises of the argument. That is, an argument is valid if and only if it is impossible for all the premises to be true and the conclusion to be false. To deduce new statements from statements we already have, we use rules of inference, which are templates for constructing valid arguments. Rules of inference are basic tools for establishing the truth of statements. Consider the following argument. If you buy a ticket, you can fly to Frankfurt tomorrow. You buy a ticket, therefore, you can fly to Frankfurt tomorrow. We would like to determine if this is a valid argument. That is, we would like to determine whether the conclusion, you can fly to Frankfurt tomorrow, must be true when the premises, if you buy a ticket, and if you buy a ticket, you can fly to Frankfurt tomorrow, are both true. Notice that the previous example is the same as saying that when P is true, and if P then Q is true, there is only one case left for Q, which is true. Another way of finding out is to look for the truth table of if P and if P then Q, then Q. So let's take a look at this. Now here we have P and Q, and then if P then Q. Notice that we have true, false, true, and true. And then if we have P and if P then Q, it would be P and if this other column. So true and true make it true, true and false make it false, false and true make it false, false and false make it false. And then finally, let's go to the last column of this table and notice that it is if P and if P then Q is always going to be true. Notice that it would be going that way, right? So true and true make true, false and false are true, false and true are true, and false and true is true. So this is what's called a tautology. That is something that is always true. In particular, when P and if P then Q are both true, then Q must be true, as is clear from the first row of the table. Let's now take a look at example 5.9. Suppose that the conditional statement, if you score more than 80% on your final exam, you will receive a grade 7 for the whole term, and its hypothesis, you scored more than 80% on your final exam, are true. Then, by modus ponens, it follows that the conclusion of the conditional statement, you will receive a grade 7 for the whole term, is true. An argument is a sequence of statements. All but the final statement in the argument are called premises, and the final statement is called the conclusion. An argument is valid if the truth of all its premises implies that the conclusion is true. On the other hand, not if P then Q is logically equivalent to P and not Q. That is, the negation of an implication is a conjunction and not an implication itself. For example, if x is an integer, then the negation of the sentence, if x is odd, then x squared is odd, is x is odd, but x squared is even. This can be seen from the truth table. So notice that from this column here, we can see that the negation of an implication is a conjunction.